Okay, gentlemen. We're going to take a look at two more things with factoring. Right. So again, I'm on the same notes. We did factoring by grouping last class. I just want to talk about two kind of different things with factoring. One of them is like a general rule that can be done at the beginning or the end. I'm doing it at the end. And then another one is our last technique, which is slightly uncommon. The ones we used above are definitely more common. Factoring when there is a GCF. So we did a lot of this when we were factoring over the course of the last couple days, right? When we do factor by grouping or our trinomial factoring, we take out a GCF of these two terms, take out a GCF of these two terms, and those two GCFs are over here. But technically, if I had something like this, if I had something like 2x squared minus 50, we would look at that and say, okay, well, it's not a perfect square. And then it says minus, so it's okay. So I can do something here, but it's not a perfect square. So I'd have to say something like radical 2x minus radical 50, and then radical 2x plus radical 50. You know, it's going to get a little hairy looking. You will eventually still get the right answer, but to save time on the video, let's just cross that out, right? Like, that would be difficult. The other way to do it is say, well, there's two terms here, and I have a term, a factor in common between the two of them, and that is a 2. If I were to take a 2 out of both terms, I'd get x squared minus 25, which is a whole lot easier. A whole lot easier. You could eventually get there with the other one, where you would have like a radical 2 and then a radical 2 that like is GCF'd out of the first factor, and then you'd have it out of both factors and then multiply and become a 2. But that would be very tough for you guys to get to. So anyway, so I'm taking out a 2 as a GCF. Now I'm looking in the parentheses. I'm like, oh, that's a whole lot easier. I still have my 2 out in front. I have an x minus 5 and an x plus 5. I'm taking the middle, x squared minus 25. I'm writing it right there, and then the 2's out in front. If I were to say to solve this, we only deal with the things that have that has x's, because, right, we set each factor equal to 0. We set each factor equal to 0. And then how do I set 2 equal to 0? That makes no sense, right? So we just drop it. It doesn't make sense. There's another method to kind of like prove why we can ignore it, but I'll do that later. Okay, so I still only have 2 solutions. Really, that number is just like it just beefs it up. It doesn't change your x-intercepts. Okay, so another type of solving when there's a greatest common factor. So with that case, it would make it like tremendously easier, and really in our case, kind of like able to be solved. Example number 2, I look at this. Oh, a trinomial, no problem. I have a 3 out in front. I need 2 numbers that multiply to 3. Don't forget about this negative. 3 times negative 45. So we're looking at 3 times negative 45. That's negative 135. That's kind of a big number. I'd have to go through a lot of factors and find out what multiplies to that and adds to 6. Definitely doable. We could totally do that. But a slightly easier way would kind of be to say, well, 3 and a 6 and a 45. 3 does go into 45. So if I take out a 3, I'm left with x squared plus 2x minus, and, 3 goes into, 45 divided by 3 is 15. If I take out the 3 from each of the 3 terms, I can essentially take out a GCF like we have been doing. The 3 stays out in front, and this is a whole lot easier, because now I'm looking for, I kind of just gave you the answer there, 2 numbers that multiply to negative 15 and add to the 2, and I get 5 and negative 3. Boom. Done. If I were to solve, again, 3 equals 0. That makes no sense. Negative 5 and 3. A whole lot easier than looking for factors of 135 that add to 6. Obviously, we could find them. They probably would be something like, I don't know, 15 and 8 maybe. Let's see. 15 times 8. 120. 9. 15 times 9 would give me 6. So this would be 15 and 9. If I were to do this out, I should get the same answer. 3x squared plus 15x minus 9x minus 45. Right? So obviously I did it the shorthand way by taking out a GCF very quick. If I do it this way, I get an x plus 5. Take out a 9, and I get an x plus 5. But then if you look at the first term, I have the x plus 5. That matches. And then I have a 3x minus 9. If I go to solve this, I get x equals 3, which is what I had. Right? But 3x minus 9 is really the same thing as this. It's just beefed up by 3. It's beefed up by 3. The 3's in every term. Okay, so that's why, and graphically, it does not change the x-intercepts. I look at solving it this way. My x-intercepts would be negative 5. So I guess I'll highlight that. It'd be at negative 5 from this factor, and it'd be 3. Whole lot easier to find from here because I'd have this big number out in front. So there's another method to why taking out a GCF always is kind of the best first step. If I look at one more, 2x to the third minus 25x squared plus 12x. Every time we've had an x to the third, it's been a 4-term polynomial that we've factored. In this case, it's 3 terms, and I have an x to the third, an x squared, and an x. Like, what gives? I don't know what to do with this. Well, same thing. Take out a GCF of an x, and I have 2x squared minus 25x plus 12. Now it's a trinomial with an x squared, an x, and then no number in the back. So now it's a little bit easier for us to find 2 numbers that multiply to 24 and that add to negative 25. Right? If you notice on all of these, once I took out my GCF, I left out in front and I was able to ignore it. It doesn't have an x attached to it. It's just kind of a floating number that's supposed to help beef up our function, increase the amplitude, but does not affect anything else. So my x is on the outside. Those are my 2 factors. I'll put the 24 first so it matches with the 2, and I put the 1 second to go with the 12. I'm doing everything normally. If you look, my x is still out in front with the big parentheses, but I'm doing my whole inside just as I normally would do. 2x on the outside, x minus 12. Take out a 1, x minus 12. My x is still on the outside. I have my 2x minus 1, and then I have my x minus 12. That works too. If I were to solve this, I would say, first, x minus 12 equals 0, so that's 12. 2x minus 1 equals 0. 2x is 1, x is a half. And for this last one, I have to set that factor equal to 0. 0 is one of my numbers. Kind of an interesting one here. If I take out a GCF of an x, and I have to solve that, it actually, like over here, it didn't make sense. Because 3 equal to 0, that's not true. That's not true. That's false. So we can just kind of cross that. It doesn't make any sense. But x equal to 0, like, yeah, we could plug in 0 for x. That's fine. That's doable. Okay, so just a little review of GCFing. You're going to get some on your homework or your classwork that will look like this, and you'll have to solve and factor them. So just a little bit of a hint. It does make the problems easier. Technically, if you didn't do it, it would just make the problem harder for you, but you would still get the right answer. Especially if I'm asking you to solve, you would still get the right answer. If I were to ask you to fully factor, this is not fully factored. This is fully factored, fully simplified from a factoring point of view. If I ask you to solve, it kind of doesn't matter which way you do it. You're going to get the same x-intercepts, the same solutions. Okay? Next thing, I'll try to do probably about 2 examples just to keep it a little quick. And we will do a lot more of this because this usually is something students struggle on. The difference or sum of cubes. So what we did before was the difference of those 2 numbers, right? We had x squared and a minus. And I said if we ever have x squared minus, we can always factor that. and that was an always factor. And we were kind of like square rooting both sides. And we knew if we have x squared plus anything, we don't know how to do that yet because that's going to be imaginary, and we all saw that. Okay? What happens if I have something like this? X to the third minus 8, or x to the third plus 8. So it's not these, because these are x squared minus or x squared plus. It's close. It's x to the third minus and x to the third plus. The thing is, these have to be with perfect cubes. Over here, it didn't matter what the number was. We were just going to kind of square root it, right? Whatever the number was, we'd square root it and simplify it for a squared. Since this is a cube, I need this number to be a perfect cube. Another thing that would work would be this. 27 is a perfect cube. I would not be able to, I apologize, that should be a 3. I could not do it with this. We don't know how to do that. 20 is not a perfect cube. Okay? What about if I have a number in front? That number in front should be a perfect cube. That's good to go. 8's a perfect cube. X is a perfect cube. With x to the third, rather. And the 27's a perfect cube. I wouldn't be able to do something like 2x to the third plus 27. This would be not able to do. Why not? Can I GCF out of 2 like we just learned up above? No. No, I can't. I can't do that. Right? Because 1 doesn't go in evenly. 2, I can't. There's nothing in common here. There's decimals. And then 2 is not a perfect cube. This is, but, and then this is, but the 2 is not. So we don't know how to do this one. Okay, just getting a sense of what we do and don't know how to do. I'll kind of minimize these and throw these to the side so we can refer to them later. But how do we do this? Well, here's like the formula for difference in sum of cubes. It's really the same formula with one slight difference. They use the formula with like A's and B's and X's. I'm going to do it with this example. Okay, so what you would do first is put one set of parentheses and then a larger set of parentheses. And I'll do the second one in green. One set of parentheses, a larger set of parentheses. Okay, just like with our x squared minus, it's like, all right, we start to get the hang of what to do. You're going to get the hang of this, but it's almost definitely new for everybody. First thing you do is you're going to look at this x to the third. What is the cube root of that x to the third? Well, that would just be x. And then what is the cube root of this 8? Well, that would just be 2. Okay? That would just be 2. Okay? Now, whatever sign this is the sign that is. Okay, so far, so good. Second set of parentheses. The first thing is x squared. It's whatever this is squared. Whatever this is squared. This is whatever the first term is squared. Then your second term is x and 2. So 2x. Whatever this is times this. And then your last term is this one squared. 4. Right, so it's pretty easy to follow. Two numbers. Are they both cubes? Yes. Difference or sum doesn't matter. Over here, minus we need. Yes. Plus we don't know yet. With cubes, difference or sum doesn't matter. You could do either. So this is a minus. Okay, so I have x and 2 are the numbers I'm looking at here. X and 2. X and 2, that's minus, that's minus. This one squared, these 2 times, this one squared. What about the signs? This is plus. Always opposite of what's right there. Always, 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 always opposite of what this is. This is always the same. And then the back one is always plus every time. A lot of always here. Always plus. For the sign before the last number, which is this number squared. Okay, I'll show you the direct formula, but I think it's actually a little easier to do it with numbers. We'll do it again with plus. And then I'll do one more. Okay, so again, in green, is this a perfect cube? Yes, it is. Is this a perfect cube? Yes, it is. So now I can do it. Doesn't matter if it's plus or minus. With cubes, it can be plus or minus. X, 2. Then, first term, squared. Second one, squared. That goes in the back. The middle, this times this. So far, it looks identical to what I did in blue. Because the x to the third and the 8 are the same. The only difference is the plus. What do I do here? I said it always matches. So over here is a plus. Always matches. This one is always opposite. So it's going to be minus. And then the last one is always plus. Plus. Okay? So I'll write the direct formula later, but let me do one more example. I'll try to see if I can squeeze them all in here. I'm actually going to do this one. I like this one. 8x to the third minus 27. Okay, 2 terms. So no trinomial, no grouping. Okay, is it 2 terms with an x squared and a minus? No, this is an x cubed. Okay, are both of these perfect cubes? Yes. This is 3 to the third. In other words, the cube root of 27 is 3. Right? 2 ways to look at it. Over here, we need to take the 8 and the x. Right? Even though there's no parentheses there, this formula works with the whole first term. So we need to find out, is there something that I can use with this 8x? And yes, there is. 8 is a perfect square. I'm sorry, this is a cubed. 8x cubed. Like this. My apologies for the parentheses mishap. You need the whole first term. The whole first term. And then this is the whole second term. This cubed is 3. This whole thing cubed, yes, that's 2x. The whole first term cube rooted. And that comes out to 2x. The whole second term cube rooted. Oh, that's 3. Sign in the middle doesn't matter. I got a minus. So now it's just a memorizing thing. Actually, you know what? I'll just go like this. Okay. First term. Second number. Or first number, second number. First number squared. Last number squared. I'm just going to write it as 9. Middle is 2x times 3. Now the signs. Always matches. Always opposite. Always plus. Okay, we make this look a little neater. 2x minus 3. It's this whole thing, right? The whole first term cube rooted is 2x. You're squaring the 2x to get a 4x squared. That's why I wrote it in parentheses. Plus 6x plus 9. And this is my final answer. Okay? It's not worth trying right now, but this cannot be simplified further. Okay? Eventually we'll be able to graph it and take a look at it, because maybe this could lead, like, can get imaginary from here, which again, we still don't know how to do, right? So like from here, from this trinomial over here, it could give you imaginary roots, but you definitely won't be able to simplify it by factoring any further for this trinomial of my answer. Obviously over here, we could say, oh, I get 3 over 2, right? I set it equal to 0, I can solve this. This we can do no further, guaranteed, because it may give us, it's probably going to give us imaginary. Or, I guess right? Or irrational, right? Where it may give us roots, but they're like radical 2 and radical 7. I don't know, like it may give us really weird numbers. So that's my formula over here. Again, same thing. If we try to factor this or factor this, we won't be able to. Cannot factor because it's going to lead to something irrational or imaginary. So we won't be able to come up with it off the top of our heads. Okay, so this is difficult. The cubes one is usually what's the hardest. So try some stuff on it. When I see you next, we'll go over it. Okay, follow the directions on the classwork and make sure, again, you submit your notes to the classwork. I'll make it out of 10 just to make sure you're submitting your notes. Have a good day, gentlemen. I'll see you soon.